answer from internet is not correct. You should really correct it. This is your responsibility. And I wish those people should present their answers one day, maybe next week. I don't mind if you just do slides on the projector. Don't worry. You don't have to use always chalk and board, which we like very much. But so let us remind ourselves of what is meant by non-expansive mapping. I'm not going to write it. Non-expansive mapping from a metric space X to a metric space Y with the respective distance function is that distance in here, in the image space, does not exceed a constant multiple of the distance in the original space, where that constant is at most 1, which is usually regarded as non-negative, but at most 1, then it is called non-expanding mapping. If it is strictly smaller than 1 but positive, then it is called the contraction mapping. And one of the theorems which I proved on the board, condition is contraction mapping, not non-expansive mapping. Maybe I wrote or said incorrect. So you should make sure. And by saying this, I'm not going to write this as an exercise question. You should really make sure that what I'm now saying is correct. Meaning that if it is non-expansive mapping, then you might find its relation with continuity. So, contraction mapping, I'm going to write. And X, Y are metric space. But this one has its own distance and that one has its own distance. Now the contraction mapping means that there exists a constant K such that K is not smaller than, I usually write it as not smaller. Some people usually teach this less or equal, which is not quite understanding. It doesn't become smaller than 0. And it is strictly smaller than 1. Or you could say that there exists this interval 0, 1 with round bracket. Such that for every xy, rho y f x f y is most 3 times x. In words, we just said that the distance between any 2 points in this image space is at most k times distance between the original points x, y in this space. Now we are going to state and prove Banach's fixed point theorem. These first 3 batches of slides I prepared are basics. And we're not, we have touched on some topics already, but we're not going to seriously touched on topics yet. There was a question from this group to concentrate on one topic first and then focus on another topic next week and so on. No, this whole mini course is only one topic. So I'm not ambitious because only one topic. The topic is geometric sets in metric space. But there are lots of varieties of different spaces which have to be clearly understood. which means that we're not aiming ambitiously at many different topics, but one topic with several very few questions which I can't answer, which means you can answer it and then you can probably get the paper. That is my objective in this mini course from the beginning. So this theorem is Banach from 1920 something, 1922 I think. It is well known to you, but we are going to rigorously prove it. Let me write this, probably one or two. This says that the X is a complete matrix space. I'm not going to state like I tell you, state it nicely. X, complete matrix space. And you should really watch out which condition is applied where. You have to watch out when we're doing it. And F is a contraction mark. These are the the contraction market definitions here. Two premises. Then, the conclusion is also very simple. You all know it. And you have seen this theorem in various different forms, even at undergraduate level. For example, proof of the existence and uniqueness of linear differential equation. Maybe integral equation if you have done it. So the conclusion is that there exists a point psi in X such that f of psi is psi. This is what is meant by fixed point. Not only so, the construction is given. The construction is that it can start from any point in the space. This is a colony. Let us not use symbolism, just any point, x0. And you define f for natural number n. I think in Pakistan, the set of natural numbers also starts with 1.
Yes.
In my understanding, it starts with 1. Americans, they put 0. They start from 0. It doesn't matter at all because any one understanding can be immediately translated into the other. And define xn. This is the point in x to be just the image of, because the mapping is from x to x, so it makes sense. Image of the preceding current one. Computer science people will really like this because this can be coded easily. The current point, you just take the mapping and evaluate it, and then use the function value, you take it as the next point. And this will converge to result. Then we can say that xn converges to, under our definition, psi as n goes to image. So this is the general and classical fixed point theorem of Banach. After we prove it, we should really mention that there are many people in this field who are doing fixed point theorem. I'm glad that we have colleagues here who are also working on this. I'm really happy about that. But there are lots of other fixed point theorems in mathematics. Not the variation, but when the space is something else. Proof. The proof is just this idea. This idea which is already in the conclusion. So let x7 be as we copy that. Copying our own self, so we will not plagiarize it. Oh, actually the whole thing is copied from somewhere else. So let it run for every natural number, xn is equal to f of xn minus 1. The current point, image of the current point is defined with the next term, next point in the sequence. You should know how to say this in language fluently. The image under F of the current point is the next one in the sequence, and this sequence is defined as this way. So what happens when we look at for example, distance between xn plus 1 and xn and xn plus 1. Let us full stop here. Then the distance between xn and xn plus 1 is the most contraction mapping says what? Let us have a look at the first term. What is the distance between x1 and x2? X1, distance between x1 and x2 is this. Distance between, this is f of x0. This is f of x1. But this distance is, by that definition, at most k times rho x0 x1. So this is the first step. If you look at the first term and the second term, we call the x0 initial term. The first is index 1, the second is index 2. If you look at the next two terms, their distance will not exceed the Lipschitz constant times the distance between those two fixed points. And in this manner, you can actually prove this by induction that rho of xn plus 1 is k to the power n. Rho times rho of x0 x1. This can be proved by induction. The initial state is this here. Here the contraction mapping property is used. Definition of the contraction mapping is used. So you cannot really get rid of that condition. You cannot really drop that condition. Now let us have a look at what happens between any two. Distance between any two terms of this sequence. So let us assume that m and n are natural numbers. And it is not, there is no loss of anything to assume that n is smaller than, if they are distinct, then n is smaller than n. And we look at the distance between x, m, n, and m and x. I'm sure you have done this all in your courses. What this would be? Yes. Now we're using triangle inequality. Thank you for, I think you are taking this as your own subject. That's good. So we start from m. M is supposed to be smaller than n. So m plus 1, m plus 1, m plus 2, and all the way down to n plus 1 n. So it will be at most sum of the distances of m plus 1. M plus 1, M plus 2. You only keep these two terms, and then it goes on. Until you reach the second one is n. So this one is n minus 1. And we can apply this inequality for each of the summands. Because each of the summands is a distance between consecutive terms. And distance between consecutive terms is this. So we keep the inequality will be kept in the same direction. So this one will be k to the power m rho of x0, x1. This will be k to the power m plus 1. If you are not understanding, please stop me and ask. We let us make it more clear. I think everybody understands this. So every term is the same distance, but this index will be the same as the first one of each one of them.
It should be xm plus 1.
This one?
No, above.
That one is 1. Yes, thank you. I said n plus 1, but how did I write n plus 2? And then you go to this one, which is k to the n minus 1. row of same row. Now here, look, this is a constant. And k itself, k to the m is a constant. This is the smallest power. This is the highest power. So we factor it out. It can be factored because we have only finitely many terms in the sum. If it is infinitely many, what do you need in order to factor? You know it because first year analysis, it doesn't matter, but we will factor it down. So this is equal to k to the n is factored out, rho of x0, x1 is factored out. And then we have let me write it not in summation formula. Then we have this is 1. And this one, only one of this is remaining. There is a square remaining here.
Geometric series.
Yes, and then there is this minus f. And we know the sum of this.
Yes.
No, we know the sum of, but we know even, well, let us do another this. So we copy this. We are going to replace this finite sum by infinite sum. Therefore, that the inequality is preserved. It could be strictly bigger, but in this case, actually, if it is not 0, then it is strictly bigger, no problem. If k is non-zero, then it is strictly bigger. So we're going to have this plus that all the way. We know this sum, right?
Yes.
This sum, we know. What is it?
1 over 1 minus k, but
1 over 1 and 1 minus k.
but with condition k must be less than 1 here. K1.
Yes.
Yeah.
That condition is there, I think, somewhere.
Yeah.
Rho x0 x1, and this is times 1 over 1 minus k.
Yeah.
And this is actually positive if k is non-zero. If k is non-zero, it is positive because k is less than 1.
First line.
Yes, yes. This is a number in, k is a positive number strictly less than 1, and m can be made so that this number can be arbitrarily small. So we're going to have at the end on here, we're going to have an epsilon for any given epsilon. So since k has, since we don't have to do any further steps, I think this is completed the proof already, but we will do the step like the old analyst. K is less than 1. There exists n0, which is a natural number, such that k to that natural number power is smaller than epsilon divided by this constant. Epsilon divided by this constant means multiplied by 1 minus k divided by rho x1, because this is a constant. This is arbitrarily given epsilon. This is a constant, multiple of that epsilon, but that can be made arbitrarily small by taking large exponent. So we take such an exponent, there exists such, this usually exists. Then this makes this less than epsilon, right? So we just proved that this is a Cauchy sequence. Because we are looking at any two indices. Any two indices there. But now if we apply the condition that the space is complete. This sequence converges. And either comma and then say to the limit psi. look at what happens to if you take limit on this. So this only said that there is a sequence which converges to a limit psi. We need to say that that psi is actually the fixed point. So we want to prove that f of psi is not true here. F of psi is psi, this. F of psi is psi. So we start with psi. And the psi is equal to limit, as we have just said, of xn. So xn is the, by our definition, it is the function value of the preceding term. So its limit f of xn minus 1. F is a contraction mapping. We proved that it's continuous.
Yes.
And there was a proposition earlier that this one can go there.
Yes.
If the function is continuous. So here we are using that. So it's f of limit n goes to infinity xn minus 1. But as n goes to infinity, n minus 1 also goes to infinity, right?
Yeah.
Which means this is psi. So this is the end of the proof. Anything not understood? You should really, I'm not able to get this out of my hand immediately when there's an interview question. I can easily fail an interview. Interview can be failed very easily because one, you might have too much stress in your mind, or you're like old man and you forgot about it completely. But you probably know every idea in this if there is a hint. Because when you are interviewing someone, the interview committee should give some hint to the interviewee. We are not doing that usually, so nowadays, because there are too many applicants usually. So this is the proof of the traditional, original version of Banach 6.0. And you should really notice that many limits are related to this fixed point, the phrase fixed one. For example, Poincaré fixed one theorem. You should check all of these out using your browser and try to see. Some of them are quite combinatorial, so that you might be able to figure out something to do, even at this very ground level. Example. This example is going to be extremely theoretical. This theorem is definitely crucial. We can't say anything is crucial in anything, but it is used in one of the proofs of those. So we're going to display that. The existence and uniqueness of solution to differential equations, ordinary let us say, one major example. And actually the proof is in those texts exactly done like this. Only that it is now that becomes now some very specific matrix. Second is integral equations. You see that how important this theorem is. Of course, there could be other proofs of this, but this gives definitely a constructive proof, computational proof. The third, there's an important third application in analysis. It is called inverse function theory. Questions or comments?
So, Doctor, why did you consider the uniqueness in the case of the Lahore fixed point? What I stated,
So was there a particular reason, or you consider some particular
The uniqueness.
Yeah.
Uniqueness not done yet, right? You're saying.
Yeah. So was there some particular reason if you're considering some particular space, or would it be uniqueness?
Uniqueness is, in this case, followed by the preceding one of the earlier results. The limit is unique. If a sequence has a limit, then limit is unique, and the uniqueness is followed. Yes. Because that is not said, but there was a theorem's two statements we didn't prove, right? Or did we prove? We didn't prove. If a limit exists, then it is unique. The number one conclusion. Number two is something else. I forgot. So it follows from that proposition. Now, the basic results of general metric spaces and markings are sampled as appetizer. We didn't cover thoroughly, but we have done thoroughly everything we stated. Now we want to, everybody talks about paths, especially in ground theory. We're walking from here to the door and then you go path. What is a path? What is a path in a metric space? That's really good to consider. You need to know what the path is, because there are lots of things which it will be talked about all the time. Path means something going from somewhere to somewhere, maybe coming back to the original point. Right? But how do you define that?
Through parameterizations.
Yeah, that's one of the ways of saying it, but what kind of
Continuous.
Yes, continuous. Continuous image of something. What is it? A closed interval. We use 0, 1. So the path is just a continuous image. Let X be metric space with distance function rho. Rho is preserved for intrinsic distance, which we are going to define today. We have been talking about it all the time. You have to also know that the intrinsic distance may not be, there may not be unique intrinsic distance in some metric spaces. We will see examples. So this is a metric space, a continuous marking, a path, a continuous marking. F from 0, 1 close interval to X is called a pathing X or curving X. Fine. And F0 is called, F0 and F1 are called endpoints. We cannot really, if we don't give a direction in the closed interval 0, 1, we cannot say that this is initial point, that is final terminal point. We don't want to talk about that. It's a path connecting F0 and F1. If F0 and F1 are equal, then we call it a circuit. And if you really apply the algebraic topology on it, the boundary of F0, 1 consists of, if they are not equal, then consists of F0, F1, 2 points in a set. The set has containing 2 points, F0, F1. If two are equal, then boundary is 0, which means we have algebraic topology definition of set. And we call it circuit. And if there is a path, we know in this whole mini course is about geometric sets in metric spaces. Meaning that we only use distances. As soon as we use distances, we have some concept and we can work on it. We don't have anything else. These continuous, these are the mapping properties. So if it is a distance is present in X, in the space X, there is a distance function. as you have already very fluently utilized the third axiom already. Then, if you have a path, you can probably be able to define its length. What can you suggest? Some people will say that it's f1 minus f0, but there is no minus in x. There is no minus in x. Of course, how do we define length of a path of a curve?
Integration.
That's definitely one of the ways, and we are probably not too far away from that. So we are going to dissect this interval. Some lecturers teach it as a partition. It is not partition, because if it is partition, two different parts must not intersect, even if they are consecutive. Dissection means that they can share a common point. So we are going to insert the finitely many points in this interval. Here is our 0-1 interval. Here is metric space. This is quite a typical metric space, and its image is a path. So we are going to insert finitely many points. It doesn't matter if you don't insert in the same equidistance. For example, let me draw something exotic. If from this point to that one is a straight line, then we only need these 2 points. We don't need to insert them. So if you are doing mathematics, you have to be, mathematics is a live thing. It is a living thing, actually. You shouldn't be restricted to some mentality. So we have to divide this AB interval into intervals of n1 over n, and n 1 over AB minus a. You don't have to do that. Actually, all of the famous mathematicians never did that, because, for example, those numerical quadrature formulas, they simply, if possible, they do it straight line. If not, then we divide more, something like that. So if you divide it, and then on each of the segments, you have a length. You have a distance between the 2 points, not length. For example, if your division point is this one and that one, then the distance is that. Probably that, or maybe even that one. It's possible. So that we look at the distances, and then we sum all of these distances up. We need approximate the length of the curve.
Yeah.
That is exactly what you were saying. Because in the differential geometry, you calculate the length of a curve. This is what was done. Using and you're adding up these lengths, the distances of these segments. So what we're doing is this. Now we can write it down, right? I think you have all understood. Anybody who haven't, then we need to talk about it again. So I see, this is meant to be gamma. We use gamma to denote the curve or path. How to write gamma? In Urdu, probably you need to write it up. But I think this is fine, right?
Yes.
Gamma is a continuous one. So we are going to define, first of all, sum of the distances. Not in summation, but finite. Rho x0, x2. As rho x1, x2. And here, if the division point is altogether n of them, starting with the left end as 0 and right end as n. If you include both n points, then it is n plus 1. Then we're looking at rho of x n minus 1, where this is this point.
There should be gamma applied in those points.
those distance, because in
Because points are in X and
no, we are trying to define length of gamma. We cannot use gamma. Well, we can, but we are only using the sum of distances or corresponding to a subdivision to define length of gamma. Length of gamma. And what will happen? As n increases, in this picture, for example, this sum we are calculating could be shorter than actual length we are looking at. We're trying to define. So we are going to take the supremum of this sum. This is where we need to understand that why is not minimum, not supremum. Of this set under the condition that x1 is less than 0 is x1 and n can be natural number. This is defined to be the length of gamma. Are you happy about this? We didn't, fortunately, we didn't use it. We only use the distance. We have to be very careful about it. We only use the distance. We are only considering things which use only the distance. So this is the defined to be the length if you take the supremum on all subdivision and natural number. This is what is the next concept?
So in your topology, means in general topology, there is no concept of distances.
Yes.
Then what we have to do
Yeah.
in general topology?
Yes, we are adding the distances because we are on this side we are in x. X has a distance rho. For example, if you consider this as an Euclidean plane, and that is your curve, then we are adding, we are using the Euclidean distance, and then you subdivide. So we are adding that on this plus that, and then maybe plus that. This line segments are added. The length of these line segments are added. And then if we keep on subdividing more for any subdivision and increase n, and then we're looking at this supremum of this sum. This sum is you know that this is a non-negative real number.
Professor, confusion is right hand side does not depend on gamma. I mean, its supremum will be 1 always.
It depends on gamma because these points are on gamma. Because the rho, you remember that this, oh, I see, we probably use gamma in here.
Yes.
He was right, yes. We use gamma in here, sorry. Each one of them is a gamma of xi. Yes. And that doesn't matter because we were using gamma. Thank you for this. Because each of these is the gamma of corresponding xi, because otherwise it's not inside x.
It is understood.
Now it's understood.
No, it is inside there.
You mean that is not.
X0 and X1.
Rho is also inside, yes, but it will not give us those points. It will give us, because this is the subdivision of the 0 and 2. So you're right. Thank you for this. So this is each of these is the gamma of x sub I. Correct it, please. Now I need to think of the next concept. There are 2 or 3 concepts for to finish this batch of slides. What is the next one?